Introduction to Singly Linked Lists. So, welcome to the lecture on Singly Linked List. It is a fundamental data structure that is important in the world of programming and in the field of computer science. So, we've looked at arrays, but unlike arrays that store elements in a contiguous block of memory, Singly list, singly linked lists consist of nodes linked together by pointers, and each node is a standalone object containing data and a reference to the next node in the sequence. And this structure allows for efficient insertions and deletions, as it doesn't require shifting elements as in an array. So we will look at the internals of a singly linked list, how it's traversed, and the operations we can perform on it. Here, if you look at the Python code, it's a one of the common definition of a singly linked list node. You can see that it's in Python class called list node, and it's usually initialized with value and next. So node structure, let's start with the uh, building block of a singly linked list, which is a node. So when we represent the node, we usually use a class including a key component, uh, a data field to store a value, and a next to reference pointing to the subsequent node in the list. So by having this dual component structure, it, we are allowed to not only store element, but we are enabling the dynamic nature. What we mean by dynamic nature is we allow linked lists to grow or shrink as needed without the need for reallocation or resizing. And this is the what's different about linked lists compared to arrays, which have static data structures. So let's now talk about the head node, because in a singly linked list, uh, in a in a singly linked list, uh, usually you want to start at the head node. So head node isn't just any node. It's basically the starting point to the rest of the list. So head node holds the first element's value and a pointer to the next element. So when we talk about the list, uh, we're essentially referring to this head node, and it's the starting point for any operation, uh, whether you're traversing the list, adding new elements, or removing existing ones. So understanding the role of the head node is really important if you want to manipulate singly linked lists effectively. Traversing the list. So traversal is a one of the fundamental operations in singly linked list. Uh, it allows us to access and manipulate the elements. However, unlike arrays that we might be familiar with, arrays you can element you can access elements directly by their index. Linked list elements are usually accessed sequentially. Uh, you would have to start from the head node, and then you need to follow the chain of next references from one node to the next. So this linear approach of traversing means that accessing a random element has a time complexity of n, with n representing the total number of nodes. So this may seem very inefficient compared to arrays. Yes, it is. Traversing can be inefficient. Traversing and accessing specific element can be inefficient, but there is benefit in linked list for other operations such as insertion and deletion, uh, and this could often outweigh its drawback. Inserting a new node. So insertion is where singly linked lists truly shine, especially when we know the node we want to insert after. So this process is very straightforward and efficient. What you want to do, step first, is to create a new node, link it to the subsequent node, and update the previous node's next reference to point to this new node. And this operation uh, has a time complexity of O1. It's This is O1 when only the previous node is known. So you can see the efficiency of linked list in dynamic data manipulation. So adding a node at the beginning. Um, Adding a node at the beginning of the list is a common operation that involves a few simple steps. Create the new node, set its next reference to the current head, and then update the head to point to this new node. This basically places the new node at the front of the list, making it the new head. And this operation not only demonstrates the flexibility of linked lists, but also maintains the one time complexity. Deleting a node. Deletion in singly linked list requires locating the node to be removed and its predecessor. Once identified, we bypass the target node by updating the uh, predecessor's next reference to point to the target node's successor. And this operation removes the target node from the list. So while finding the predecessor requires traversing the list, uh, it will result in a of n time complexity. So, but the actual deletion process is efficient with a space complexity of 1, since it requires only modifying pointers. Deleting the first node. So deleting the first node in a singly linked list is a special case of deletion that's uh, even more straightforward. Since we know the head represent the first node, we simply need to update the head to point to the second node. So this effectively removes the original head from the list. Conclusion. So singly linked list uh, is a versatile and dynamic data structure. Uh, and this data structure is ideal for scenarios where you need to have a efficient insertion and deletion operations. While linked list compared to arrays may not offer the best performance for direct element access, uh, their benefits in terms of dynamic memory allocation and data manipulation often make them a very useful tool for programmers. As we look more into linked list in future lectures, we will learn even more about their applications and advantages in solving complex computational problems.